So good afternoon, everyone. Let me start by thanking the organizers for this wonderful meet and inviting me, and also somehow thank Shriram to make me think about this broad area, which started off as a project with one of the graduate students in TI for Hyderabad, and somehow it keeps on surprising me that we keep on finding more and more new things in something that Shriram and Aditi started doing in 2002. So that's what the story is going to be about. Um, so the title is A Novel Instability, Waves and Turbulence in Polar Active Fluids. Let me start by a disclaimer because there are people in the audience who are experts in turbulence. By turbulence here, I just mean chaotic motion. Don't worry about cascades and other things. Huh? And when I say a novel instability, what I will point out to you that this is a instability which is different than the instabilities that have been talked in previous talks, where the fact that you have organisms which are extensile or contractile and have stresses which they impose onto the fluid matters. Okay, so let's go ahead and see what is the instability and what is new thing about it. Somehow, you see the pointer, guys? Okay, good. So, okay, this work was mainly done by Purnima, who is a graduate student at TI for Hyderabad, and Navdeep, who is now with Raman, and they have been really, the main drivers behind this work, and of course, Shriram. So let's go ahead. So what I'll be talking about are active polar suspensions, and large number of organisms fall in, or rather all organisms which have head-tail asymmetry fall in this class. And to me, I won't worry about for the time being, and just be with me that whether they are extensile or contractile, we'll just put them all together. Any organism that swims is polar. And they come in different size shapes, and one of the things as a fluid dynamist one worries about is the Reynolds number. Typically people look at swimmers at extremely low Reynolds numbers where you are in the Stokesian regime, whereas I would be thinking of suspensions where you are at Reynolds number order 1, so the inertial effects could be important, and so that's what I would request you to keep in mind. So let's go ahead. So what are the equations of such swimmers or organisms? These equations were put forth by Aditi and Shriram and way back in 2002. And so you have the Navier-Stokes equations, which gets coupled, which describes the hydrodynamic velocity field of the fluid plus swimmers. Because these are organisms which are polar, there is an equation for how does the polar field evolves in time. There is a contribution because of the self-advection. Then you could have concentration variation, which gives you osmotic pressure-like term gamma E grad C. Of course, because you have swimmers inside, there are both active and reversible stresses in the system. The active stresses are typically extensile or contractile, and of course, because you have a concentration field of yeah. Oh yeah, thank you. So yeah, omega is antisymmetric, grad U minus grad U transpose. Otherwise, that would be fun. Okay, anyways. So, and because you have the concentration variable, right, it gets advected by the hydrodynamic velocity field, and of course, there is a self-propulsion, right? So these are the fundamental equations which many people have looked at. And so what is the typical question that one asks? The typical question one asks is the following, that let's say a collective suspension of such organisms which are ordered, right? One could think of a uniaxial order. Let's put some small perturbation on it, like so, and ask the question whether such a system stabilizes or destabilizes, right? And if it destabilizes, then what are the eventual states, what kind of chaotic states this one gets in, right? Now let's ask why should such a system stabilize or destabilize? And well, many earlier studies are there, and they point out that look, active stresses are crucial, right? Whether extensile or contractile, but active stresses are crucial, and they destabilize flocks, right? Especially in the Stokesian limit, right? Activity completely drives the flock unstable. More recently with Shriram, we found out that inertia could stabilize a flock, at least in the Malthusian and incompressible limit. where we found out that in the limit of, if there is large enough inertia, then the swimming speed can win over the instability that is which the extensile stresses or contractile stresses give in the system. Well, I'm wrong. So instability in the extensile limit, the contractile instability remains, but inertia. Sorry. Okay. So, but inertia, at least in the Malthusian limit, can stabilize the flock, at least in this setting. So let's go ahead and let's ask the question, what would happen if the active stresses are weak or absent? So let's look at the extreme scenario where you have the same equations which we looked at earlier, but there is no, no contribution because of active stresses present in the system. So you have just a suspension of swimmers which are swimming, going around, making some collective motion. But the crucial difference is the reversible stresses are still present, right? And let's ask the question whether such a suspension is stable or unstable. And what I would like to point out is a crucial thing, that the activity is of course still present via the motility term in these equations. Oh my God. Okay. Is the pointer working? Somehow. Okay, let it be. Yeah, that's okay. So, but one thing you have to realize is that the way things are, if you have by some mechanism, if let's assume that you form some gradient or some local accumulation of concentration, then if because of the E grad C, the osmotic pressure like term present in the system, if E is less than 0, then the polar term P would order itself in such a way that it will enhance the formation of more and more concentration. On the other hand, if E is greater than 0, then it will push things away, somewhat similar to what happens in the standard Navier-Stokes equation in the ideal gas limit, right? So let's keep that in mind. With this, let's go ahead and let's ask the question which we looked at earlier. That is, let's assume I have an ordered suspension of particles, right? And I'm looking in the Stokesian limit. And let's ask the question whether this suspension is stable or unstable. You do the standard linear stability analysis and you get the dispersion relation which is given here. And what you find out is immediately that the first thing is that if E is greater than 0, you have damped waves present in the system. The waves are moving with speed, which is the first term over there. On the other hand, if E is less than 0, then the first term will lead to an instability and you could have accumulation of concentration. But this instability is known in the literature. This is very much MIPS-like instability, the motility-induced phase separation kind instability. So that's not a surprise. Let's ask the question, what happens in the limit when E is greater than 0, right? And let's look at the system with inertia now. Let's look at the full system in its glory and let's ask what happens to the instability. Again, we'll start with the orientationally ordered flock, add perturbations to it. You write down the, the linear stability equations, and for simplicity, let's just look at the pure splay perturbations, as at least we have found out that they are most unstable. You get some dispersion matrix, but crucially, what you find out is that you now, for E greater than 0, have something which is remarkable. You have first something which is a wave, which is like a toner 2 wave, but you have additional term present here, which in certain limit can go unstable, right? So now we have a system which is a suspension of motile organisms. You don't have active stresses. Yeah. What's your background flow? 0. So you start with, the base flow is the organisms are all oriented. So it's orientationally ordered flock. U is 0 and the concentration field is homogeneous everywhere. You now add perturbation to it and ask the question, what's happening to the system? Thank you. So what you're finding out is that, remarkably enough, the moment you switch on inertia, there is an instability which appears in the system. And this instability looks strange because it requires you to have 3 things. Typically, most instabilities you look at, you are just looking at competition between 2 things. And now here, you are in a system where you need 3 things together working in cohesion to give you something which is remarkable. What are those 3 things? 1, there should be coupling of order parameter to the concentration field via the osmotic pressure like term. You should have the motility, right? And you should have inertia. Any one of these 3 gone, the instability vanishes, as I showed you earlier for the Stokesian system, right? E less than 0, we won't worry about it in this talk because I already pointed out to you that goes order Q unstable. It's MIPS-like system, right? So for this talk, let's only look at E greater than 0. And as I point out, this is the new instability, right? Which hasn't been looked at in the literature before. Now let's ask the question, what is the mechanism of this instability, right? It's easier said that there is an instability, but what is the mechanism? How does the system drive itself, right? So let's look at a minimal model. What you do is you take the more complicated equations here and then look at system which is homogeneous in x direction, and you can simplify it, and so you can write a minimal model which is written over here. It's easy to see then that the Stokesian regime is rho is equal to 0. Their velocity and concentration are trivially related to each other. You can, for this minimal model, you straight away therefore see that the concentration gradient and the polar order parameter behave exactly in the identical way, and both of them, if you bring them together, act as a relaxation term. So any variation in concentration gradient is relaxed by the polar order parameter via this term, right? So now let's ask the question, what happens if I now take inertia into account? And then something which at least Purnima and Navdeep found out with lots of numerical simulations and looking at things closely came out, which was that inertia introduces a time lag between the order parameter and concentration. So when the order parameter is trying to relax the concentration field, you have the velocity pumps in between. So it's like a delay equation where one term is relaxing and other term is pumping in, and that one could easily see by looking at the Pearson correlation, which for the Stokesian system would be just all in phase, whereas the moment you have inertia, the two things, you get a value which is less than 1. Indeed, if you plot the velocity and the polar order parameter and concentration field, at times you find them out of phase, at times you find them in phase. More remarkably, if you do the numerical simulation of these equations and look at a particular wave number mode, you see a close Lissajous figure. So on the x-axis is py, concentration and the velocity field for a given wave number mode, and you see a Lissajous-like figures. Let's ask the question, can we understand this, right? So for that, you have to go beyond the linear stability, and that's what you do in the standard dynamical systems. You look at the amplitude equations, and for simplicity, let's just look at a particular amplitude. That's what Purnima did. You assume a simple solution form, plug it into these equations, you get an equation for amplitude similar to what Landau does. And once you have that, you can ask what is the solution. You can come up with ansatz, which is similar to asking if the system has a Fourier kind of a solution to it. And so Purnima came up with this simple ansatz that let's assume C is like this, P is so, and U is so. Then what is the question is, once you have obtained this, or you believe that this is truth, you want to find out what is C1, P1, and U1 and omega. And Purnima found it out. Of course, there are not one solution, but two solutions come here. One is a trivial solution where C, P1, and U1 are 0, and the other one is a non-trivial solution where you get, so if you plug in omega, the frequency is square root of gamma EV1 times Q, then the other things follow. You can exactly find out what is P1, C1, and U1 over there, as well as the phase. And the phase here, remember, is pointing out that U and the concentration field are, or the order parameter field, are not in sync with each other. That's the crucial bit, right? So the moment, so this simple 1D model clearly tells you, using some analysis, that there has to be a phase difference which comes in because of inertia. And indeed, within this simple model also we found out consistently that in the Stokesian limit, no inertia, there's only trivial solution when there's phi 0. Inertia leads to a non-trivial solution. We can show actually that it's a limit cycle. What you get is a closed thing. There is a Hopf bifurcation as a function of either density or the E variable. The black colored, sorry, the red dots are the results of numerical simulation. The colored circle is the analytical solution obtained from CTPTUT, right? So it matches quite remarkably well. Now let's ask the question, this is all for simple systems when you were doing 1D, trying to understand what is the mechanism of instability. Now that you have figured out that there is a new instability, let's ask the question, how does the system behaves when you do the full scale simulations. So that's what Purnima did on really large scale boxes, because you want to resolve not only the large scale structures but also the small scale structures. And because we wanted to do high resolution simulations, I think some of them are also at 8,000 square. We did as GPU parallelization. That's nowadays everyone does. So what we are going to do is we are going to keep all the parameter fixed and just change the parameter E, which remember is like a osmotic pressure, and E is going to be greater than 0. What one finds out is that the kinetic energy, which is given by red dots, goes on increasing as you increase E. The variation in the concentration goes on decreasing. And if you look at the polar order parameter, it goes from something which is nearly ordered to disordered. And so I'll show that some of these things are there. What we have figured out that when E is small, you see wave-like behavior. Then there is a crossover regime where you would see waves as well as defects, polar defects present in the system. And finally, at large enough values of E, you see turbulence. But this turbulence is slightly different. And I'll tell you what this turbulence is in a moment. Okay, so let's first look at what happens at small values of E. On the left, you have a movie which shows you the concentration field superimposed with the polar order parameter. Okay, and you see straight away that there are waves which are traversing. There are actually two different waves. On the right, you see one of the waves. So what we have plotted is the gradient of the concentration, which is going in this direction. So you just draw this contour, draw normal to the contour, and that's the direction of the wave. All right. Then you could ask the next question that can I determine what is the speed of the wave and what is the gap between these two bands? And that's not too difficult actually. What you found out is that the speed of the wave as we vary E is quite in good agreement with what you would expect dimensionally. It goes indeed like square root of gamma EV1. And the distance between the bands actually decreases, and again that's consistent dimension, what we expect dimensionally. So that's great. So we find out that there's first regime where in the system you would have waves which are traversing through each other. These waves don't interact, they just go through each other, and we can estimate what is the wave speed and the spacing between the waves. In the intermediate regime, something remarkable happens. You have large fluctuations in the concentration. You have something which is at times looks like a nearly ordered state, but then spontaneously you start to see appearance of polar defects in the system. And so you have something which is now showing signatures of something chaotic is going to happen, right? So let's look. Then we finally said that okay, let's increase the value of E further. So now you crank up to larger values of E and you look at the concentration fields and you see something like ocean waves. So ripples moving through the system, truly beautiful. And these ripples don't interact with each other, they are not dispersing, they're just going through each other. On the other hand, if you plot the polar order parameter, and if you had just shown you polar order parameter, you would have said, hey, look, it's defect turbulence, as is known in the active matter community. So on one hand, when you are looking at concentration fluctuations, you have waves which are going through the system. On the other hand, if you look at polar order parameter, you have defects present at large scale. Clearly something multi-scale is happening. There's something which is happening at small scales, there is something happening at large scale. Can we do some characterization of that? So that's what we did. And so what you do then is the following, that look, I see something where there are multiple scales involved. And from at least my experience in turbulence, I know that, if there are vortices, it looks incompressible. Why don't I take the order parameter field and decouple into using what is called as a Hodge decomposition into a purely potential part and the incompressible part. The compressible part is, or the potential part is plotted on the top right, and you see something like asters which appear in the system. Of course, the incompressible part shows you vortices, all right? So there are at least two different things happening simultaneously. Can there be a signature of that which is, you can quantify properly? So you plot the energy spectrum of the polar order parameter field, and what you get is quite nice. So at small enough wave numbers, you have E of Q going as Q, which indicates that the system is, completely, you can model the system as something like a white noise. Remember, this is 2D, so you expect for Q going to 0 when things are completely decorrelated. This is shell average spectrum, that would go as Q. For scales which are, so the peak of this thing, the spectrum appears at the integral scale of the vortex. So at the right of that, at scales which are large Q or scales smaller than vortex sizes, right, intervortex separation, you would expect Porot scaling to appear. There you would expect something going as Q raised to -3. We start to see close to that, Q raised to -2.5. What is the right peak? Well, if you look at the compressible part, the interaster separation appears to be around, what is the scale, LE, which is mu over square root of gamma EV1. So that's the scale at which things are getting pumped in, and that corresponds to interaster separation, and that peak comes up here. And then of course, it falls off quite rapidly. Again, something similar to Q. So that's the picture where at large E, values of E, you have turbulence, but this is a bit different turbulence than what one sees in active matter literature typically. You have two scales simultaneously or you have turbulence at two scales appearing simultaneously. We don't completely understand how we would characterize it more. Are there cascades of order parameter and other things? We haven't looked at any of that. So several questions that in principle one could look at. So with that, I think my time is also up. So I'll stop and I'll conclude by saying what I've pointed out or showed to you, that in the system, which Sriram and Aditi showed in 2002, there is still a novel instability which appears quite remarkably because of the interplay of inertia, concentration, and motility simultaneously. You are not required to worry about whether the organisms where, or the suspension is contractile or extensile. In both the classes, you would see the instability. We somehow characterize the things with the control parameter E, which is the the coefficient in front of the osmotic pressure term. In the polar order parameter, and small values of E, you see traveling waves. At large values of E, you see multi-scale turbulence-like behavior with waves in the background. We haven't characterized it more, but that's something that we would like to do it in futures. Thank you.
I have two questions. One is, why is Q to the -2.5 quasi-poro? What does it mean?
No, I'm not saying. I'm saying it's close to. We don't have enough scaling range there to say that whether it's -3 or not -3.
The other question might be stupid, but can you reach a regime of wave turbulence in these systems?
Sorry?
Could you reach a regime of wave turbulence in these systems?
So I don't know in this system, and that's my honest answer, what would be the regime of wave turbulence? No, but you see when
interacting non-linearly.
So that's what Rahul's question was, and all I'm pointing out is that the simple amplitude equation analysis that we did gives some hints that such a description might be possible, but we haven't done it in detail, because then you have to couple multiple waves, you have to see what interactions you keep, what interactions you don't keep, and whether one could write down something which is an effective amplitude like equations, like what is done in a typically wave. So that's, I think, long road to go to that.
Thanks. Very interesting talk. In the wave simulation video, you had these triangular patterns going through each other. We looked at a system with non-reciprocal alignment interactions, and there you also see something like that.
Oh, is it?
And I'm wondering if there's any relation between those, because somehow you can argue these quorum sensing type interactions give persistence to the direction of motion, which could be also similar to what inertia does. But this is very superficial at this point. So I just wanted to point this out. And there we saw very clear sensitivity to shape of boundary or boundary conditions. So my question is, did you check that if you change the aspect ratio, or I don't know, put a hard wall or something, you would still have this kind of feature?
So hard wall I haven't done. The aspect ratio is a good point. I'll check that. But I am very sure that this will go through, because we have gone to the extreme aspect ratio of 1D, where you are able to see most of the phenomena again, at least, but not the full waves going through in 2D. So we will do that. My feeling or my guess is it would go through, but yeah, I need to check it.
Okay, yeah, let's talk about this because we see something new appearing when we change the aspect ratio, even similar to the Turner 2 type flock and the formation of a band with the fixed width and some more features. So it's a very interesting. I mean, it looks innocent, but it's a very interesting feature.
Sure. Thank you. Yeah, we'll talk.